So for the first one, the t-statistic was pretty large. We reject the null for these within equation restrictions on capital. For labor, the t-statistic is pretty small. Again, I don't even need to look it up, given the number of degrees of freedom. We don't reject the null, so the restrictions hold there. For energy, the t-statistic was quite large. You would reject the within equation restrictions. For materials, testing the symmetry restrictions. So this is the question here is whether or not your estimate of gamma 1, 2 in one equation is the same as your estimate of gamma 1, 2 in another equation. So you take the difference of the two. You think under the null, the difference between the two is 0. And by construction, the two random variables, gamma hat 1, 2, from both places are statistically independent of one another. You constructed it that way. You assumed that the covariance between the error terms in the two equations was 0. If you had assumed it was something other than 0, you would have had to change the construct of your estimator. So by construction, you made it independent. So we only needed the own variance terms out of the two coefficient covariance matrices. So the first symmetry, it looks like gamma 1, 2, gamma 1, 3, the symmetry restriction is satisfied. Gamma 1, 4, that's a pretty big t-statistic. And that's probably on the borderline at about the 95% level. Gamma 2, 3, again, the symmetry restriction is not violated. Gamma 2, 4, 2.6 is a big t-statistic. I would reject the null that the symmetry restriction holds on 2, 4. Now I forget what my notation was. I don't know if that was. I think that's energy and materials. Turned out, as you went through this, and many of you noticed this, that materials and energy turned out to be kind of problematic for some of the adherents to the formal notions of economics. Going into it, I would have expected some problematic results for capital, because capital, we have a problem in that output is a flow variable. It's number of widgets per period. So because the dependent variable is a flow variable, the things on the right-hand side ought to be flow variables as well. We don't buy a machine for owning the machine in its own right. We buy the machine for the flow of services that the machine throws off. Unfortunately, because of the way that data is collected, often capital variables are capital stocks. And the consequence is that we have real trouble statistically with investment equations and production equations and cost equations that involve capital, because we should be using flows and not stocks. The other three variables are less problematic because labor, for example, is usually reported as the number of people per period. And so that's sort of a flow. Energy, for sure, is a flow. It's kilowatt hours. How many kilowatts did you consume over the 24 hours that you were running the plant? How many tons of materials did you use per period? So the materials variable is often a flow as well. So if you were to pursue this broad area of research in the future, these are things that you have to think about. Am I mixing stocks and flows in the models that I'm trying to use? And it's a common problem. Okay, but I didn't trouble you with any of that business. Some of you did note in passing that some of the numerical results involving, I guess, capital and materials were problematic. So derive the Allen elasticities. If you looked in the footnotes in your textbook, all you have to do is run the Uzawa's paper, 1962 paper, and out it popped. Some of you found another source for finding this, and so I just checked to see whether or not you had the end result. Okay, there's nothing special in doing it. It's just algebra for the most part. Deriving these results. Although not all of the symmetry restrictions are rejected, we'll construct the Allen elasticities for the multiplicity of estimates. So there was a reason that I asked you about the symmetry restrictions. If the symmetry restrictions had held, we wouldn't have to look at the Allen partial elasticities from two different perspectives. You could have done one test and been done with it. So the way I did these tests was to, and I suggested in the homework that we think of the factor shares as non-stochastic. That means that in each of these Allen elasticities, the only random variable is the estimated coefficient. So because, so I guess I combined two parts of the homework here. You see the numerical estimate of the Allen partial elasticity on the left, and then the corresponding t-statistic on the right. So in the upper right corner of the board there, you can see that the Allen elasticity is 1.234, and then it's the variance of that Allen elasticity relies on your recalling that the variance of a constant times a random variable is the constant squared times the variance of the random variable. So that's why the denominator looks the way it does. If you separate out the two pieces of the fraction, the denominator is the same in both pieces, and the statistic, the realized statistic, is 0.00049 divided by the constant, 0.046 times 0.044. So it's the square of the constant times the variance of the random variable, and that's the t-statistic. There are two other things you could have done. You could have said, another way to approach it would have been to say, well, I have my null hypothesis is that gamma ij plus si times sj over si times sj is equal to 0. You could have said, for example, I could restate the null hypothesis, because I don't like excessive computation. I could restate the null hypothesis as, that's the same null as gamma ij plus si times sj is equal to 0. So you could have done it that way. And then, which is the same as writing that gamma ij is equal to si sj, which is some number. So the test of hypothesis is about comparing gamma hat to si sj, not comparing gamma hat to 0. A bunch of you wrote something like, well, I know that gamma hat was statistically different from 0, so therefore the elasticity is statistically different from 0. Well, no, that's not what the comparison that we're making. Minus SISJ. We're checking to see whether or not gamma ij is different from minus SISJ, not different from 0. So I don't think when I graded that, I wasn't too heavy-handed. I just took off a point. There are a couple of people, well, there were a bunch of people who were, again, I didn't penalize them heavily. I thought it was, they were thinking, at least thinking creatively. They said, well, I have 25 years of data, so in principle, I have 25 different observations on this random variable that I'm going to call, I guess the symbol we were using was sigma ij, right, for the partial elasticity. Yes. So I have 25 different estimates of sigma ij, so my test statistic is the average of the sigma ij hats divided by the standard error of those estimates. And so they figured from the 25 sample observations on the sigma hat ij, they computed a sample standard deviation divided by the square root of n, which is 5. And so that's my t-statistic. If they had thought about it for a little bit, they would have realized that they got the denominator wrong. The numerator was okay. It's okay to take, if you want it, you could take the 25 sigma hat ij, average them, but then you have to go back and look at what made up the sigma hat ij. The sigma hat ij was gamma hat ij plus SISJ over SISJ. And so you need the standard error for that, not the standard error for the 25 observations on the sigma hat ij that you had. So you were headed down the right road, just at the very end, there was a little slippage. So again, I wasn't too heavy-handed taking off points because I thought it was a clever way to approach it. You just got to be more careful about asking yourself, what's the random variable? What's the definition and construct of the random variable? And then, what's the variance of that random variable that I have constructed? And it's not just the sample standard deviation of the sigma hat ij over the square root of 25. There's a little bit more to it.